What if two particles could be separated by millions or even billions of light years, and their quantum states could still be correlated? Not connected by light, not connected by any signal traveling between them, just linked instantly, no matter the distance. It sounds impossible. It sounds like science fiction, but this isn't fiction. It's one of the most well-tested phenomena in all of physics. Scientists call it quantum entanglement, and it has survived over 60 years of increasingly rigorous experiments designed specifically to break it. So here's the question we're actually asking today. If entanglement can stretch across a laboratory, could it stretch across a galaxy? Could it stretch across two? I'm Deep Space Files, and today we're finding out just how far the strangest rule in physics is actually allowed to reach. Let's start with what entanglement actually is, because the popular version you've probably heard is usually a little bit wrong. Here's a common analogy. Imagine you have two gloves, a left and a right, sealed in separate boxes and shipped to opposite sides of the planet. Open one box, and you instantly know what's in the other. No signal, no delay, just certainty. That's the intuitive version, but it's imperfect. And here's why. With the gloves, the outcome was already decided the moment they were packed. Quantum entanglement doesn't quite work that way. When two particles become entangled, their properties become linked in a way that isn't fully determined until a measurement is actually made. Measure one particle, and the outcome of measuring the other becomes statistically correlated with it, correlated more strongly than anything. Classical physics, on its own, can fully explain. And here's the part that made this discovery so strange in the first place. Distance doesn't simply erase that mathematical relationship. Separate the particles by a few feet or by thousands of miles, and the correlation, in principle, persists. That single fact is what unsettled some of the greatest minds in physics. In 1935, Albert Einstein, along with physicists Boris Podolsky and Nathan Rosen, published a paper that would echo through physics for the rest of the century. Their argument was simple, but powerful. If quantum mechanics was correct, it seemed to allow correlations between distant particles that had no obvious explanation within the framework of classical physics. Physics built on the idea that objects have definite properties, independent of whether anyone measures them. Einstein wasn't objecting to the math. He was objecting to what the math seemed to imply about reality itself. He famously dismissed the phenomenon as spooky action at a distance, not because he believed something was secretly traveling faster than light, but because he suspected quantum mechanics was simply incomplete. He believed there had to be some hidden information, some deeper variable, that would restore a more familiar, predictable picture of the universe. For decades, this remained a philosophical disagreement. Brilliant physicists arguing about the nature of reality with no way to actually test who was right. That changed with one theoretical physicist and one remarkably clever idea. In 1964, physicist John Stuart Bell found a way to turn Einstein's philosophical question into something that could actually be measured in a lab. Bell showed that if Einstein was right, if hidden variables were secretly determining the outcomes all along, then measurements on entangled particles could only ever be correlated up to a certain mathematical limit. But if quantum mechanics was right, that limit could be broken. This became known as Bell's theorem, and it turned an unanswerable philosophical debate into a testable prediction. Scientists could now build real experiments, take real measurements, and simply check which prediction the universe actually followed. Since the 1970s, and especially in incredibly rigorous experiments conducted from the 1980s onward, the results have been remarkably consistent. Entangled particles violate Bell's inequalities again and again, exactly the way quantum mechanics predicts. This work was significant enough that it was recognized with the Nobel Prize in Physics in 2022. But here's the part that's absolutely critical to understand, because it's the single most common misconception about this entire topic. None of this allows faster than light communication. You cannot use entanglement to send a message, a signal, or any usable information instantly across space. The correlations are real, but they only reveal their pattern when you compare results afterward, through an ordinary, light-speed limited channel. No shortcut, no exception. So if entanglement is real, and distance doesn't erase it, where exactly does it start to break down? Scientists have pushed this question further and further. First across a lab bench, just a few meters apart. Then across a city, using optical fiber. Then, in 2017, Chinese researchers used the Mikius satellite to demonstrate entanglement distributed between ground stations more than 1,000 kilometers apart, a genuine milestone in experimental physics. So if entanglement can survive meters and kilometers and satellite-to-ground distances, is there theoretically a fundamental distance limit at all? Based on our current understanding of quantum mechanics, the mathematics itself doesn't impose a hard distance cutoff. But here's the critical distinction, and it's one worth sitting with. Entanglement can exist across distance, and entanglement can be practically maintained across enormous cosmic distances, are two very different statements. One is a question of physical law. The other is a question of engineering, environment, and practicality. And that second question gets dramatically harder the farther you go. This is the heart of today's question, so let's be precise about it. There is currently no experimental observation showing that two entire galaxies are quantum entangled with each other. That's not a modest way of saying, probably not. It's simply not something physics has ever claimed, tested, or observed. Here's why. A galaxy isn't a single particle. It's an almost incomprehensibly large collection of stars, gas, dust, and radiation, constantly interacting with everything around it. Every one of those interactions, every stray photon, every collision, every bit of radiation bouncing around has the potential to disturb a fragile quantum state. Physicists call this process decoherence, and it's the reason delicate quantum effects tend to vanish almost instantly in large, complex, noisy systems. Maintaining entanglement isn't just difficult over long distances. It's difficult in the presence of almost any interaction with the surrounding environment. And a galaxy is, in every sense, an incredibly noisy environment. So, the honest answer isn't a simple yes or no. It's this. Individual quantum particles, say, two photons produced by the same distant astrophysical event could, in principle, remain entangled across enormous distances if nothing along the way disturbed them. But that's a fundamentally different claim from saying two galaxies, as entire systems, are linked. Nobody has demonstrated that. And based on what we understand about decoherence, it would be staggeringly difficult to prove, even if it were somehow true. But this raises a deeper, more unsettling question. If quantum mechanics governs particles everywhere, does that mean the universe itself has some kind of quantum description? In a sense, physicists already think about it that way. Quantum field theory describes particles as excitations in fields that stretch across all of space. And cosmologists trace the large-scale structure of the universe, the distribution of galaxies themselves, back to tiny quantum fluctuations that occurred in the earliest fractions of a second after the Big Bang, later stretched to cosmic scale by inflation. That doesn't mean the universe is one giant, entangled object today. Most of those early quantum effects have long since decohered into the classical structure we observe. Now, actual galaxies, actual stars, following the more familiar rules of gravity and classical physics. But it does mean something worth pausing on. The largest structures we can see in the night sky may trace their origin back to quantum-scale events. Quantum mechanics may not connect galaxies today, but in a real sense, it helped shape where they ended up in the first place. Now for the part of physics that sounds the most like science fiction but is, at this stage, entirely theoretical. In 2013, physicists Juan Maldacena and Leonard Susskind proposed a striking conjecture, now known as ER equals EPR. The idea connects two seemingly unrelated concepts from 1935. Einstein-Rosen bridges theoretical tunnels through space-time, more commonly known as wormholes, and Einstein-Podolsky-Rosen entanglement, the same phenomenon we've been discussing this entire episode. The conjecture suggests that entanglement between two black holes might be mathematically connected, in some deep theoretical sense, to a wormhole linking them. Let's be absolutely clear about what this is and what it isn't. This is a theoretical proposal, explored through the mathematics of quantum gravity and string theory. It has not been experimentally confirmed. It does not mean entanglement functions as a travelable wormhole. It does not provide any method for faster-than-light travel or communication. And it remains an active, unresolved area of theoretical physics, debated among researchers who study the deepest connections between quantum mechanics and gravity. It's a genuinely mind-bending idea, but it belongs firmly in the category of fascinating hypothesis, not established fact. So, after all of that, where does this actually leave us? Quantum entanglement can, in principle, produce correlations across enormous distances. That part is genuinely established physics, tested and confirmed repeatedly. But that is a very different claim from saying two galaxies are physically linked by some invisible quantum connection. What's established? Entanglement is real. It violates Bell's inequalities exactly as quantum mechanics predicts, and it has now been demonstrated over distances stretching more than 1,000 kilometers. What's possible in principle? Individual entangled particles could theoretically maintain their correlation across even greater distances, including astronomical ones, if nothing disturbed them along the way. What remains speculative? That entanglement links entire galaxies together, that it creates any kind of physical channel or connection between them, or that concepts like ER equals EPR describe anything resembling a usable, traversable link. None of that has been shown. Some of it may never be. Maybe the strangest thing about quantum entanglement isn't that it lets one particle instantly affect another. It doesn't. Nothing here breaks the speed of light. Nothing here sends secret messages across the void. The stranger truth is quieter than that, and in some ways more remarkable. Nature allows correlations between distant quantum systems that classical physics, built on our everyday intuitions, simply cannot fully explain. That fact alone has survived 60 years of the most rigorous testing science has ever thrown at it. Two galaxies may be separated by millions of light years. Physics gives us no evidence that they're quantum mechanically linked, but quantum mechanics does remind us of something worth sitting with. Distance doesn't always mean the universe behaves the way our everyday intuition tells us it should. Somewhere out there, entangled particles may still be carrying a quiet, correlated secret between them, born the moment they were created, indifferent to how far apart the universe has since pulled them. We haven't found two entangled galaxies, but we've found something almost as strange. Proof that reality itself doesn't fully respect the boundaries. Distance is supposed to create. If you want to keep exploring the strange physics hiding behind the universe, subscribe to Deep Space Files. Revent is happening right above your head.